Welcome to this lecture number 25. This is mostly the tutorial for week 5 on irrigation and drainage series lectures. So, in this we are going to solve some of the problems related to sprinkler and drip irrigation. Okay. So, in the example or exercise 1, so in a sprinkler irrigation system, right. So, the system is sprinkler irrigation. So, the lateral spacing along the main line is 20 meter and sprinkler spacing along lateral is 15 meter. Okay. See, the application rate for fulfilling the peak demand of the proposed crop should be 8 mm. Find the discharge rate for the sprinkler. So, this is the question. So, what is the discharge rate for the sprinkler? So, in this, so spacing is given, right, and the peak demand is given 8 mm per day. Okay. So, you have spacing, right, and peak demand 8 mm per day. So, in that case, so what is the discharge rate from each sprinkler? Okay. So, that will meet the 8 meter per day. So, here I mean the formula is very simple. If you see we know the application rate I is equal to, right. So, the Q s is the discharge rate at individual sprinkler divided by the spacing S m into S L. So, this is unit conversion in a way. So, then the discharge rate at the sprinkler, which is equal to application rate, right, into the area. So, all values are given like I mm per day, right. So, values are given, but only thing is you have to see whether the units are in proper order or we are taking the same kind of units or not. So, assume that the sprinkler will operate 12 hour per day. Okay. So, this is another thing. So, let us assume the sprinkler is being operated for 12 hours. So, I is given, that is mm, suppose 8 mm is the demand. So, and 12 hours. So, you get 0.667 mm per hour. Okay. So, this is the application rate and S m is 20 meter, S L is 15 meter. So, the putting the values, you get Q s is equal to 0.055 liter per second. So, then that will be 200 liter per hour. Okay. So, this is a simple sprinkler irrigation problem in which if you have the demand, crop demand in a day, right, and also the sprinkler spacing. Okay. So, you can find out, so what is the discharge at sprinkler, so that can meet the demand of the crop in a particular day. So, this is an example. So, the next example here you see. So, in a sprinkler irrigation system, the required total capacity of the system is 0.5 meter cube per second. Determine the pump capacity. Assume that head loss in the pipe and bends and the velocity head required 3 meter of water. So, here discharge I mean pump capacity needs to be determined and the head loss is given, okay, and capacity of the system is 0.5. Okay. So, the pump capacity, which is equal to P is equal to, so this equation in kilowatts. So, Q into 9.81 into H. So, I mean the P power is equal to Q into H. So, the constants here 9.81 or sometimes you say 76, okay, sometimes gamma and unit weight, rho. So, all these things will come when the units you follow basically. So, this I mean on general equation you had Q into H. Okay. So, your pump capacity Q, that is meter cube per second, H meters. So, put these values directly and you get 14.7 kilowatts. So, all values are given, just put the values. So, and then the next problem here is, so a solid state permanent micro irrigation system is installed in a vegetable field of 1 hectare area. Okay. So, the spacing between the micro sprinklers is 2.5 meter and spacing between laterals is 5 meter. So, here the spacing is given and the peak evapotranspiration is 10 mm per day. So, from that particular field, right. So, that evapotranspiration, that is 10 mm per day. The application efficiency is 80%. Okay. So, irrigation system operates 5 hours in a day. So, the total operating head of the pump is 30 meter. At 65% pump efficiency, the horsepower of the pump is. Okay. So, here if you see, so we will go, the only thing, the pump head operating pump head is given. So, only thing what we have to find out the requirement. So, what is the requirement or application rate? Okay. So, from there you are going to find out the discharge to the particular discharge through the pump. Once you know the discharge and head, you can find out the the power. Okay. So, that is the thing. So, let us find out. So, what are the given? The given values are like hectares, like 1 hectare land, evapotranspiration 10 mm per day, application efficiency 80%, right. So, here suppose you have a field, this is 10 mm per day, right. So, and then application efficiency 80% here. So, right. Then total operating head of the pump 30 meter. Okay. The pump efficiency 65% is the pump. Okay. So, with this let us see in the next slide the solution is, so ET is given 10 mm per day. So, that is 0.01 meter. So, the volume is equal to area into ET. So, that will be around 100 meter cube. Okay. So, the area for what? 1 hectare. Okay. So, for 1 hectare, if constantly 10 mm is leaving the 1 hectare land. So, you need to replenish the 100 the same amount back, that is. So, the volume is 100 meter cube. So, actual volume will be, so this is in the field, right. So, in the actual the volume of water needs to be delivered to the field will be different, that depends on the efficiency of the device you are using. So, this volume divided by application efficiency, you get 125 meter cube at the field, outside of the field you have to apply. I mean, from, if this is the field, 125 meter cube if you apply, that means, so it will utilize meter cube. Okay. So, because 80%, the device efficiency is 80%. So, then actual volume divided by the time. So, 125 divided by, so you are operating at 5 hours. So, that will be 0.00694 meter cube per second. Okay. So, this, so H p is now knowing the Q and H. Okay. So, then you substitute the values, this is the density, okay, and then the efficiency 75 is the efficiency, okay, and so substituting, this is the viscosity. So, substituting all the values, you get 4.27 H p. So, this is the value of the power required by the pump to discharge Q at a head of H. Okay. So, let us see the fourth one here. Okay, so, the fourth, so several identical sprinkler nozzles. So, each having discharge of Q, that is in liter per minute, or spaced in a grid of size L meter and S meter. the application rate in mm per hour. So, this is a kind of a unit conversion. So, suppose you have a field, right, and the space at a grid size of L meter and S meter, let us say S, L and S, right, and application rate. So, what is the application rate in mm per hour if the sprinkler nozzles are identical having the discharge. So, here the sprinkler discharge is liter per minute. Okay. So, it is a liter per minute and you get area of cross area liter per minute. Okay. So, liter per minute divided by area you get per hour. Okay. So, now you manage the units. So, let us see this how the units are really balanced. See, so we know that Q is equal to L into S into I, right. So, this is the area into application rate I. So, now I is equal to Q divided by L into S. So, this is liter per minute, let us say. So, just convert that into so I is equal to, so 0.001 into 60 cube, okay, meter cube per hour. So, minutes been converted to hours, that is 60, and liters been converted to meter cube. So, that is 0.001 and liters, meter, S meter. So, all are in meters and hours. Okay. So, now 60 cube divided by L. So, this is in meters, let us say in meter, now convert it in. So, this since everything is in meters and hours, now convert this in cube, right, per hour divided by into So, 0.001 into 60 cube meter cube. So, if you want to convert this into so this will be 10 power 9. Okay, so, this will be 10 power 9 cube per hour, and here 10 cube into 10 cube. Okay. So, ultimately you get 10 cube because 6 gets cancels out, 10 cube cube per hour divided by into multiplied by 60 into 0.001 okay, 60 into 0.001. So, then since it is 10 power minus 3. So, this gets cancels out and 60 cube cube by hour. So, finally, you get 60 into Q divided by L into S per hour. So, I is equal to 60 Q into L into S per hour. So, this is the answer. Okay, so, now exercise number 5. So, in this there is a sprinkler system consists of two 192 meter long laterals. So, there are two laterals here. Okay. So, the lateral length is 192 meter and one each lateral. 16 sprinklers are located at an interval of 12 meter. Okay. So, there are 16 sprinklers, they are located at 12 meter interval and the distance between the laterals is, this is 10 meter. Okay. The required capacity of the sprinkler system for application rate of 1 centimeter per hour. So, if the application rate is 1 centimeter per hour, so what is the Q value? Okay, what is the Q value? So, the same we know that Q is equal to this is the equation, Q is equal to S L into M into I divided by 360. Now, you have to put the values, right. and finally, so you get system capacity, which is the total. So, you get Q is equal to this much 0.333 liter per second per sprinkler. So, since you have 32 sprinklers, okay, since you have 16 sprinklers on each, total 32, we get 2 lengths and you get 10.56 liter per second. This is system capacity. All right. So, now this is the last example. If you remember the in the drip irrigation. So, the based on the pressure and the discharge. So, you can knowing the coefficients, you can identify whether the dripper is orifice type or laminar type or it is a pressure compensating type. Okay. So, that is the so Q is equal to K into P power x, right. So, knowing the x values, if x is equal to 1, that is a laminar, x is equal to 0.5, that is orifice type, x is equal to 0, that means the pressure component will be So, Q equal to K. So, there is pressure compensating drippers. So, now in this problem, calculate the flow rate for the following emitters. So, we have 3 emitters, that is a laminar flow emitters, turbulent flow and pressure compensating emitters at 50 and 100 kilopascal pressure, okay. And coefficient of K for units of liter per hour, right, and kilopascal. So, you have to find out okay. So, here the K values are given, okay. K is equal to 0.02. So, and so for a particular unit the K values are given. So, when Q is in LPH and kilopascal, that is P is equal to kilopascal and your K value is 0.02 and x is equal to 1, okay, it is a laminar case, and K equals 0.2, x is equal to 0.5 turbulent case, K equals 2 and x is equal to 0 pressure compensating case. So, this is given, okay, this data is given. So, now find out for a particular case what is the discharge. So, it is a direct implementation of the equation. So, the Q is equal to here K into x K into P power x. Okay, so, put the K value 0.02 and x equal to 1 laminar, okay, and laminar case x equal to 1 and this is orifice case and x equal to 0, this is pressure compensating case. So, Q is equal to 0.02, that is the K, and 50 is P value, okay, and there is the same thing 100 the other value. So, you get 1 LPH and when pressure is double then 2 LPH. Similarly, in orifice case, so increasing the pressure, so 50 and 100. So, this is not double, okay. So, orifice case the discharge is increasing, but not at the laminar case, whereas pressure compensating case the discharge will not vary, okay, the same even if you increase the pressure 50 and 100. So, the discharge is same, okay. Okay, so there is the last example in this. So, this is kind of a multiple choice. If you see the discharge from a sprinkler nozzle depends on, so look at this discharge from the sprinkler nozzle. So, there is a sprinkler nozzle, right. So, the discharge from the sprinkler nozzle. So, that depends on operating pressure and nozzle geometry, operating pressure and distribution pattern, application rate and nozzle angle, operating pressure and application rate. So, these are the options given. So, the first option if you take operating pressure and nozzle geometry. So, definitely when you are talking about discharge, so operating pressure influences, of course, nozzle geometry influences. So, this possibly this could be, and then second one operating pressure, yes, the distribution pattern. So, distribution pattern entirely different, because the pattern it may vary, right. So, it may not be individual sprinkler, even if you see the individual sprinkler. So, the discharge may not be influencing the distribution pattern. This definitely influence by if you have wind speed and other things. So, this will definitely influence. Then application rate and nozzle angle. So, nozzle angle will tell the range, right. So, suppose you have 30 degree nozzle angle. So, it decides the maximum range, but not the discharge. And then application rate. So, that crop I mean we for the particular crop requirement we will decide. Operating pressure, yes, application rate, no. Okay. So, in this case, so we expect A be the answer for this. Okay. So, this is all in this tutorial, and thank you.